Okay, welcome back. So in the afternoon, we have a session for the randomization. And the first talk is about instance-wide hardness versus hardness trade-off for pass-through marine protocols and weak preview vector protocols.
Hello, everyone. Thanks for the introduction. This is joint work with Dieter. And, well, very important question in computational complexity is whether we can simulate these randomized algorithms deterministically with not a lot of overhead, right? And perhaps the most famous version of this question is if P is equal to BPP, right? We just get polynomial overhead there. Today we'll be focusing on a related question, which is, can interactive proofs be simulated now non-deterministically? Right, so if we focus on constant round proofs, this is essentially asking if NP is equal to AM. Right, so if we can de-randomize AM into NP. And in fact, there is evidence that points towards both of these equalities being true, both P equals BPP and NP equals AM. Right, so what do these look like? So Suichi talked about this a bit earlier today. These are the hardness versus randomness trade-offs. So they go more or less like this. If hard functions against circuits exist, then de-randomization is possible. Right? Since we believe these functions do exist, we believe that de-randomization is possible. Right? And the idea is that we use this hard function, let's call it f, and we instantiate a pseudorandom generator or a hitting set generator for one-sided error. G sub f, right? It depends on this function f. So what does that look like? Say we have our randomized algorithm A there, takes a regular input x, and a random sequence rho produces an output, right? So all we do is replace the random input by a pseudorandom sequence that is produced by this generator GF, right? And then as long as this function f is really hard, the output of this algorithm fools any efficient algorithm A, and you get de-randomization, right? So, okay, I'm talking about these hardness versus randomness trade-offs, where if you have hardness, you get de-randomization, right? The way we prove these types of results is actually the contrapositive, right? So we show that if the output of the generator that we have is not pseudorandom, then the function is actually easy, right? So it wasn't hard to begin with. And usually easy means it has small circuits, but it may have an efficient algorithm, an efficient Arthur-Merlin protocol. That's what we're going to have today, right? And the way this proof goes is usually via a reconstruction using a distinguisher, right? So let me first talk about this distinguisher, right? So let's say we have our algorithm A with some input x, and the generator fails to fool this algorithm with this input, fails to fool it, right? It detects the difference between the output of the generator and a truly random input. So what we do is we take these two into a little box. That's our distinguisher, right? Algorithm plus input. That's our distinguisher. And we feed this distinguisher together with any other extra information we might need about the function into an algorithm that we call the reconstructor, R, that outputs a small circuit for the function. Right? So in the end, you're showing, oh, this small circuit exists. I can even compute it, right, efficiently. And very commonly, this extra information is composed of evaluations of the function itself, and then we call the reconstruction learning. Right? So today, the reconstruction that we're going to see is learning, right? So this extra information will be composed of evaluations of f. Okay, so for BPP, right, what I've talked about until now is that these non-uniform lower bounds, so lower bounds against circuits, imply de-randomization, right? But this de-randomization that's implied is black box because you get a pseudorandom generator, produces a sequence that doesn't care about what algorithm it's trying to de-randomize or the input. It does it in a black box way, right? And in fact, we have a full equivalence between black box de-randomization and these lower bounds, these non-uniform lower bounds, right? We may ask, what we get if we assume uniform lower bounds, something like x is not equal to BPP, for example. We also get de-randomization, but then it's on the average case. And at least in some settings, we get an equivalence there as well. So if you start from average case de-randomization, you get the uniform lower bounds back. Right? But this leaves the question open, right? What if I can fully de-randomize BPP, but not necessarily in a black box way? What do I get on the left, right? And for a while, by the word of Goldreich, 2011, we've known that we get targeted pseudorandom generators that I'm going to talk about next, right? But recently, Li Chen and Roy et al. Showed that you get this different type of lower bound, which is against almost all, on almost all inputs, right? I'm going to talk about these as well. So, okay, what does a targeted generator looks like, right? So remember our setup. We have the algorithm A, input X, and a random sequence row. And we want to replace that by a pseudorandom sequence, right? So a targeted generator gets to see X as well. It gets to see the input X, and it produces a pseudorandom sequence that depends on X, right? It's tailored to fooling algorithm A on input X, right? That's what a targeted PRG is. And the existence of those objects is equivalent to de-randomization. Right? And then usually the way we construct these is by employing a hard function again, a hard function f. But now the idea is that if the function is hard specifically on input x, then the output of the generator on input x is pseudorandom. And in particular, we get de-randomization on that input. Right? So that's where the almost all inputs hardness comes from. Since we want to de-randomize, we want the de-randomization to work on almost all inputs, we end up needing to assume hardness on almost all inputs. Right? Thing is, that's actually necessary to get de-randomization. Okay, so what does this almost equivalence between these lower bounds and BPP and de-randomization of BPP looks like? So from de-randomization to hardness, Chen and Tel showed that if promised BPP is in P, then you get the existence of a function f. It's computable by uniform circuits, and it's hard for probabilistic algorithms on almost all inputs, right? So you get almost all inputs hardness from de-randomization. And in the other direction, if such a function exists, right, that is hard for probabilistic algorithms on almost all inputs, and now there's only one caveat, is that the function needs to be computable by shallow circuits, right, circuits of low depth, then you get de-randomization back, right? So that's why we have two arrows there. There's a bit of a gap in that in one direction we need the circuits to be shallow, while the other one we don't necessarily get that. Okay, so let me now talk about AM, right? So in the black box setting, we have the exact same equivalence between non-uniform lower bounds and black box de-randomization, right? In the uniform setting, things are more complicated for AM. Assuming uniform lower bounds against Arthur-Merlin protocols, we get de-randomization in the pseudo setting, and we get implications on both sides, but no equivalences are known. Is this the right type of assumption, right, in this setting? But again, we may ask, what if AM is equal to NP, right? What do we get on the left there? And I remarked that we don't even know if we get targeted generators for AM, like we do for BPP for more than 12 years now. So what we show here, our main result, is we get a similar near equivalence for AM between these lower bounds on almost all inputs and de-randomization, right? And we also get a couple of byproducts in different settings that I'll talk about later. Okay, so what does these results look like? So first, if we assume de-randomization of AM, full de-randomization, we get a hard function in NP that is hard for AM protocols on almost all inputs, right? With the caveat that it requires a few bits of advice to compute. In the other direction, if we have such a hard function in NP that is hard for promise AM protocols on almost all inputs, then you get full de-randomization of promise AM. So there's actually two gaps here. One is in relation to the advice, which is only in one of the directions. And the other one is assuming de-randomization, we get hardness against AM protocols, but we need hardness against promise AM protocols. It's like this technical distinction. And it precludes the, it doesn't allow for a full equivalence because of that, right? And I just want to mention that the hardness to de-randomization direction scales very well towards the low end for its lower de-randomizations, right? De-randomizations in sub-exponential time, for example. Okay, now for the byproducts. So we also showed that assuming de-randomization of AM, you get targeted HSGs, so the one-sided version of a targeted PRG. But there's a big loss there in the types of targeted HSGs that we get. So it's not a full equivalence yet. And we also showed that assuming uniform lower bounds, we can get average case de-randomization of AM, kind of like in the BPP setting. So not pseudo de-randomization, we can get average case de-randomization. And we also show an unconditional de-randomization result for promise AM in the average case setting in the class sigma 2. I'll get back to this later. Okay, so what does the argument for our main result look like? So starting from de-randomization, we get hardness essentially by diagonalization. So it's not the most important one. We need some advice there to help us diagonalize against non-deterministic computations, which is usually hard. Right? For the other direction, we combine two ingredients and we construct a targeted generator. Right? So these ingredients are PCPs, probabilistically checkable proofs, and the recursive Milterson-Vinochandran generator that I'm going to call RMV. It's a generator suitable for de-randomizing AM, and it's due to Chautiel and Humans. Okay, so here's a formal statement of the hardness to de-randomization direction. So if there exists this hard function f, it's in NP, more precisely in time n to the a, non-deterministic time n to the a. And if it's hard on almost all inputs against promise AM protocols running in time n to the c log squared of a, you get de-randomization, where c is a universal constant, right? So let me just parse that the speed up that you shouldn't be able to get if you want de-randomization is going from time, non-deterministic time, n to the a, to essentially n to the log squared of a. So it's almost an exponential speed up there, well, in the exponent for the polynomial. And the c is just a fixed constant. Okay, how do we prove this? Well, we're going to construct a targeted generator that is based on a PCP for the value of f on input x, right? So this function is computable in non-deterministic time, polynomial time. It has a PCP. We're going to use that. And then if our generator fails, we'll be able to compress this PCP with an Arthur-Merlin protocol. And then finally, once we have this compressed version of the PCP, we can run the PCP verifier, and whenever it needs to look at the proof, we actually use this compressed version of the proof to speed up the computation of the function f with an AM protocol. Okay, so let me just say a few things about the RMV generator. Like I said, it's this recursive version of the MV generator by Milterson and Vinochandran. And what it does, it takes as input the truth table of a hard function g, and it outputs a pseudorandom set. Right? I'm calling the function g because it's going to be different from the function f in our construction. And then if this construction fails, right, the output is not pseudorandom, it doesn't fool some Arthur-Merlin protocol, then there exists a specific type of Arthur Merlin protocol that's called a commit and evaluate protocol that computes this function G, right? And what do I mean by efficient there? It's just that if you start from a function of size around n to the a, right, like the size of a PCP for the value of f, then this protocol runs in time n to the o of log squared of a. So that's where the log squared of a comes into the proof. That's where we actually lose time because a PCP is very efficient, right? It's only when accessing this compressed version of the proof that we need more time. Okay, so what does a commit and evaluate protocol look like? Well, like I said, it's an Arthur Merlin protocol, and it has two phases. In the commitment phase, Arthur samples a random subset from the domain of this function G, and Merlin just replies with evaluations of G on this subset, right? So this is why it's a learning reconstruction. All Arthur needs at this moment are these evaluations, right, that I'm calling pi. We also call this a commitment. So once Arthur has these evaluations, this commitment pi, Arthur and Merlin can run the evaluation phase, where they interact as in a generic Arthur Merlin protocol. So Arthur sends randomness, Merlin replies, Arthur makes a decision, and they evaluate the function G on any point. That's the idea, right? So first Merlin commits to G, and then they evaluate G, right? And everything looks great here, but since it's an Arthur Merlin protocol, we need to understand what happens if Merlin tries to cheat, right? So we have completeness here. If Merlin is honest, we can compute this function G, but what happens if Merlin is dishonest, right? So we don't really get soundness, but we get resilience, which is this property that I'm going to talk about now. Right? So let's say in the commitment phase, Arthur does the same thing. He sends that random subset, and Merlin replies with some commitment tau that may or may not be evaluations of G on this subset S, right? So what happens at this moment is that after sending this response, Merlin is committed to some fixed function G sub tau that depends on the commitment. It might not be the correct function, but it is a fixed function. So if during the evaluation phase, Merlin tries to make Arthur output something other than an evaluation of this function, of this G sub tau, then Arthur is going to detect that with high probability and reject. Right, so we get some protection against a cheating prover, but not soundness. Right? So that's why we combine this with PCPs to get soundness. So okay, what does the generator look like? Like I said, it's a targeted generator. So it takes as input the actual input x and a hard function f in n time n to the a. Then what it does is it guesses and verifies in non-deterministic time by enumerating over the randomness of the PCP verifier. It guesses a PCP y that asserts this value of f of x. And then it instantiates the RMV generator with y as the truth table of the hard function. Right? So the hard function is, give me an index I, I'll give you the ith bit of the proof. Then if this construction fails for input x, we want to show that we can compute f of x efficiently with an Arthur Merlin protocol. That's what we're going to do now. Okay, so if the construction fails, how do we compute f of x? Well, we first run the commitment phase, so Arthur sends the random subset, and Merlin replies with the evaluations of G, so essentially with pieces of the proof. And also with the value of f of x. So Merlin is claiming here that f of x is equal to some value z, right? And now that Arthur has access to x, the commitment pi, and z, he runs the PCP verifier, and whenever he needs to look at some bit of the proof, he runs the evaluation protocol and interacts with Merlin to obtain that bit. Right? So it's important here that the PCP has non-adaptive queries, so we can do this all in parallel and not have many rounds of communication. And in the end, we get a 4-round protocol. We can collapse it to 2 rounds efficiently. Right? So for completeness, like I said, if Merlin is honest, he sends the correct value of f of x and commits to a proof, then the PCP verification is going to accept, and Arthur outputs the correct value. But if Merlin is trying to cheat and making Arthur output something other than f of x, then by resilience, in the first phase, Merlin is committed to some fixed proof. So when Arthur finally reveals the random bits for the PCP verification, he's going to reject because there is no proof, well, with high probability, because no proof would make Arthur accept with noticeable probability. Okay. So now for, like I mentioned earlier, we know of this equivalence between de-randomization of BPP and the existence of targeted generators. And it's been open for a while if we have these objects from de-randomization of AM. And we take a first step here by showing that any de-randomization of AM actually guarantees the existence of targeted generators. So informally, what we get is a weak de-randomization of AM guarantees the existence of targeted generators that grant us an even weaker de-randomization of promise AM. So that's where I said we have a gap, right? So to be more precise, if we can mildly de-randomize a quasi-polynomial version of AM, then we get targeted HSGs that give us a fixed exponential de-randomization of AM. So a very weak de-randomization with a little bit of advice, right? So like I said, a huge gap there, but at least it's the first indication that these objects are actually necessary for de-randomizing AM. I'll also talk about the other byproducts briefly. So we get average case de-randomization of promise AM from worst case hardness. Here's the theorem that we get. So if we can, unless we can speed up non-deterministic exponential time computations by introducing randomness and non-adaptive oracle access to satisfiability, we get de-randomization of promise AM on average, right? So again, the quantitative relationship here is similar to the other one, right? So we go from time 2 to the AN to 2 to the log, in this case, A plus 1 squared of n. So it's a substantial speed up that would have to happen for us not to get de-randomization. And I'll say one sentence about how we prove this. The idea is that if we allow for a BPP parallel set version of the reconstruction, right, of that entire Merlin commits to a proof, and then Arthur verifies the proof, we can get an even stronger resilience property that allows us to get average case de-randomization from worst case hardness. And then finally, we get an unconditional de-randomization for promise AM in the average case setting. More precisely, we show that promise AM is infinitely often in the sub-exponential version of sigma 2, NP with an NP oracle, with subpolynomial advice on average, right? So this on average is important here because if it was not there, we would get some really interesting consequences that I'm going to talk about next. And again, I'll say one sentence about how we showed this. The idea is to use this win-win argument with a new easy witness lemma for sigma 2 computations, our targeted generator construction, and diagonalization. So we combine all of those and get this unconditional de-randomization result for promise AM. So just to conclude, we've shown this almost equivalence between hardness on almost all inputs and de-randomization. And surely the most important open problem here would be to get a full equivalence, right? Can we get back this hardness that we need? We seem to be close, but not there yet to get the randomization back, right? And I just would like to mention here that the gap is different from the one that we get in the BPP setting. So it might be easier to overcome this gap, right? It might be harder as well. It's just different. And perhaps a stepping stone towards getting to that result is showing that de-randomization of AM grants us targeted generators that give that de-randomization back, right? So this would be a stepping stone, because if we have hardness on almost all inputs, then we get targeted generators, right? So this would be an intermediate step there. And to me, a really interesting open problem is the AM versus sigma 2 problem. So it seems, at least at first to me, it seemed almost obvious that AM wasn't sigma 2, right? MA is even lower there, but that's still open for AM, right? Best we know is pi 2 P, right? And we don't even know if AM is in the sub-exponential version of sigma 2P with subpolynomial advice, right? So a really nice open problem for me here is obtaining the stronger unconditional de-randomization. So the exact same de-randomization that we obtain in the worst case setting instead of the average case setting, right? So just remove the average case there and go to worst case. And if we could get that, we would get novel lower bounds against non-deterministic circuits, right? So the specific lower bound is sigma 2e is not in NP/poly. So this can be seen as a scaling up of next versus P/poly, right? So if you add one extra level of non-determinism on both sides, you get this problem right here, right at the frontier of what we know in relation to lower bounds against non-deterministic circuits. And that was the last slide. Thank you, everyone. Any questions?
Any question? So what's the intuition behind the gap you have? Can you explain?
Mm-hmm. Let me just get to the gap again. Okay. So from de-randomization to hardness, we want to obtain this function that is hard against AM protocols, right? So because we're de-randomizing, it's hard against non-determinism, essentially, right? So if you're thinking about an AM protocol that respects the AM promise on every input, when you de-randomize it, you get a single-valued computation, right? So in that case, if you have advice that tells you when computation is, which machines are single-valued, you can efficiently complement this and get hardness, right? But if you're just assuming this hardness against promise AM protocols, then you don't necessarily get a single-valued computation back. So that's where there's some trouble in this technical distinction. Oh.
Can you say something about why pairs work if you pseudo setting randomization, but you can get average case randomization?
Sorry, can you?
Can you explain why pairs work if randomization in pseudo setting, but you get average case randomization?
Okay, so maybe let me go to the slide here. Yeah. So the idea is that we want that if the de-randomization fails, we want to get a promise AM protocol computing whatever function language we have, right? So generally, what we need is to find the input in which this de-randomization fails, and the pseudo setting lets us find this, if the de-randomization fails there, you have an algorithm that produces it, a non-deterministic algorithm that produces it, right? If you just try to get average case de-randomization there, you can get a bunch of candidates, right? You can try to sample an input where it fails, and you're going to find one with high probability. But because you don't know which one it is, you need a stronger form of resilience for the reconstruction so that it works on every input, because that property that I said about resilience, it only actually holds for like no inputs for promise AM computations. Right, so when you're sampling a bunch of inputs, you may get yes inputs and no inputs, and then we don't know what to do with the yes inputs. Right, so then what we get by weakening the reconstruction a bit is that now we can deal with the yes inputs because we get resilience for those as well.
Okay. So getting average case, the randomization is stronger than in pseudo setting, right?
Depends, right? I think they're incomparable. That's the idea.